inshallah on the نبدأ. Okay. طيب. So we're continuing inshallah on the graph theory, last part, and we'll try to solve some questions today, similar to what you will get in your assignment, which is going to be posted today, and what you will get in your quiz on the assignment, which is going to happen next week, and what you will get in your midterm, which is going to happen the week after, right? يلا رمضان مبارك. ما هي جاي بالبركه الحمد لله. The week after. Okay. So the first theorem that we look at today allows you actually from the adjacency matrix to figure out between any two vertices in a particular graph, find the paths, the number of paths with certain length. And the length of the path is defined as how many edges are there in the path. Okay. So the theorem says that if you have the adjacency matrix for a particular graph, matrix A, and you want to find the number of paths with length R between any two vertices Vi and Vj, what you need to do is to go to the matrix A, raise it to the power R, so raise it to the length of that path that you are looking for, and then go to that A to the power R matrix, pick element in the row number I and the column number J, and the value in that element is going to tell you how many paths between vertex Vi and Vj with length R are there. Okay? There is a proof for the theorem. As usual, proofs are not required from any of you. So none of those theorems you will be asked to prove or anything like that, or deduce a new theorem or anything like that. We are just studying basics of the graph theory. But the proof is there just in case you are interested to read it, or you are interested to explore further or understand more or whatever. So it's just there for demonstration purposes, but it's not something that's required from you to study. Okay? And skip the proof and going to an example on that theorem. We have here the graph composed of the four vertices A, B, C, and D. And then for that graph, the adjacency matrix is given here, but I want you to deduce it yourself. So try beside the graph here to write the adjacency matrix and then compare it to the solution. So start, please. ما انا ما جيتش ناحيه اللي قبله لحد دلوقتي. انا طالب بس for this graph find the adjacency matrix. The graph اهو. Write the adjacency matrix for the graph. That's it. Adjacency matrix does not need اسامي الedges. Okay. Adjacency is the columns and the rows are the vertices, right? And then if two vertices are adjacent to each other, which means if there is an edge between those, then you put one in that row and column. If there is no edge connecting the two vertices, then at that row and column you put 0. تمام? No. This is one edge, second edge, third edge, fourth edge. Yeah, because when you type, it represents them different. I didn't ask any question other than you have here this graph, which shows that A is connected to B, B is connected to D, D is connected to C, C is connected to A. So these are the edges. These are the vertices of this graph. Please write down the adjacency matrix for this graph. That's it. I didn't ask for anything else yet. Huh? Yeah, it should look like this. But I wanted you to do it from your brain before comparing it with the answer. خلاص? خلاص يا شباب. Everyone got it and it looks the same like this one. طيب تمام. Now given that this is A. خلاص. So this is our adjacency matrix A. The question is how many paths with length 2 are there between A and D. ده ماشي 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 ماشي. كل ده you can figure it out from the graph. I want you to find this from the adjacency matrix. Okay? Yes. Go ahead. اكتب A to the power 2. So the theorem says in order to find this, what you need to do is to take A and you square it. And then after what, do what? After that, do what? So now I have A square. Let's say it's some values. Then I will do what? You go to what? To the row that corresponds to A and the column that corresponds to D. Right? So if you ordered them A, B, C, D, and A, B, C, D, then you should go to this number, and the value here should be the one that you already found out by your eyes, saying that there is this path and this path only, right? Okay. So now find A square, please. أول حاجة بس find A square. Either from a calculator or do it by hand or do it online. Find A square. اكتب لي A square. A multiplied by A. The element which is between A and D. صح صح صح. This is wrong. Sorry, element at row A, position D. This element. 2. Yeah, the matrix, yes. Yeah, yeah. Yes. Yeah. Yeah, same like this one, but with 2s instead of 8s. So, good. حد لقيها؟ مين اللي مش فاهم السؤال؟ ايه اللي انت مش فاهمه في السؤال؟ طيب سؤال يا شباب قبل ما اجاوبك على اجابه السؤال. What's the meaning of a path? Because we discussed this last time. What is a path? Huh? Yeah. So it's a set of edges that you can continuously traverse one after the other so that you can move from one vertex to another vertex. صح؟ يعني if I say the path between A and D, then I need to find some edges that I can go across them, right? Until I reach D. It doesn't have to be adjacent. It can be after multiple hops, right? The length is the number of edges that you had to go through. Okay. تمام؟ كده فهمت السؤال؟ يبقى عشان امشي من A ل D في كام طريقه بس يكون طولهم كلهم 2 بس. يعني عدد الادجز اللي فيهم اللي عديت عليهم 2. Okay. So anyone found A square? Yeah, exact pattern but with 2s. Yes, similar to the one. Yeah. And then to find that number, which one of these? From A to D. So which number of these is going to represent the number of paths? Yeah. No, you start. This is from A to D. So you start, yeah, so A, D. So this one. Yeah, it's always going to be symmetric. So if you pick this or this, it's going to give you the same thing. Okay. But لا كل ده نون دايركتد. شايف اي اسهم هنا؟ مش دايركتد في الموضوع. ايوه. لا، فين الفور دول؟ يعني دي تو ايه هي بنفسها من ايه تو تي يا جدع؟ does not count as two, counts as one undirected path. بس هو ده ولا ده؟ هو صح، الاثنين هيطلعوا زي بعض، بس هو ده ولا ده؟ لا لا، ده غلط، ده غلط خالص، هو يا ده يا ده. ما هو مكتوب لك from A to D، يبقى ايه؟ بالظبط. هو دايما هيطلع سيمتريك، ده زي ده وده زي ده. هو الثيرم دي is only for undirected paths. It's not for directed. Okay. Anyone is suffering anything or تمام. From A to D, so pick element number I اللي هو ايه هنا، ورو وكولوم جي اللي هو دي هنا بس. ايوه بالظبط كده. يس. خلاص يا شباب. ده فين ده اللي 1 زائد 1 زائد 1 4 دول؟ طيب، نظريه ان 1 زائد 1 زائد 1 يساوي 4، ماشي. دي نظريه جديده دي. طيب خلاص يا شباب. Everyone is okay with this? You know how to apply the theorem now? Makes sense? Okay. طيب, a question for you. The example solved here, okay? لو سمحتوا يا شباب concentrate please لأن الجزء الجاي ده might be confusing. The example solved here is for how many paths of length 4 between A and D. And the numbers here, لا مش none ولا حاجة. The numbers here says 8. Right? If you want to figure it out from the equation, it's 8. Where are those 8 paths? حد يعرف يطلعهم؟ طلع لي واحد. One path with length 4. ايوه. يعني كده، بعدين كده، وبعدين كده، وبعدين كده. صح؟ This is a path of length 4. The notice انا ليه بقى why I'm showing you this. Notice that the theorem does not say simple path. Because a simple path لو تفتكروا المرة اللي فاتت is a path where in each edge is traversed only once. لكن هنا it just says path, doesn't say simple. تمام؟ So this means that I can pass through the same edge multiple times. Nothing prevents me from doing this. So this is one. Can you show me the other 7? No. 1, 2, 3, 4. ما انا رايي اعملهم كلهم في جنب، هيطلع لك اربعه، والاربعه اللي زيهم الناحيه الثانيه. Yeah. So you can do this, right? 1, 2, 3, 4. Right? Okay. And you can do this. 1, 2, 3, 4. حلو. So this is لحد كده this is 3 paths. Where is the fourth from that side? ها؟ تبدأ من B ازاي؟ احنا بنقول from A to D، يعني you have to start at A finish at D. ايوه صح. So the last one is I don't have colors for it. So it's going this way and then back and then this way and then this way. خلاص. And then there is a symmetric side that you can do. The other 4 you can do them from the other side. Okay? خلاص. These are the 8. So this is 4 from one side and there are other 4 from the other side as well. لا، ما of length 4 انت مش هتمشي 50 مره، انت عايز تعمل ايه؟ هم 4 لازم يبقى end up with 4. ليه؟ عملناها اوريدي في الاصفر. We went past and then came back. ينفع. المهم ان الاند تبقى دي. The point is that it shows you all possible paths. That's the point. Yeah. With a specific length. Okay. شباب we are not in a break ولا حاجه. Move on. The next is something important, a definition of two properties of a graph which are called the Euler properties. And the graph that has one of those two properties or both of them is called an Eulerian graph. Okay. Euler لسه بعديه كمان جاي لك هامilton. بعد Euler. Next slide يعني. Okay? So there are two things that can happen in a graph. A graph can have an Euler path or an Eulerian path if you can traverse all the different edges in the graph exactly one time while starting from one point and finishing at a different point. So for example, I start from B, right? And then I go, go to A, and then go to C, and then go to D, and then go to E. Now, if I go back here, I'm stuck, right? Wala la, I'm not stuck. I can go down, I can go up, right? Stuck or lissa? Yeah, I'm finished. So I started from B, I finished at A, and I made sure that I pass every single edge only once. The edge. I care about the edges. I don't care about the vertices. تمام? There is no edge that I passed through two times. There is no edge that I skipped. I went through all the edges of the graph only exactly one time, and I started from one point. I finished at a different point. Yeah. I don't care about vertices. I'm talking about edges. I didn't pass any edge more than one time. You can do whatever you like with vertices when you are talking about the Euler properties. The next property, which is the Hamiltonian property, talks about vertices, not edges. So you can pass edges multiple times if you want, or you can skip them, right? But the important thing is you don't go through any vertex more than one time exactly. That's the next one. But for now, we care only about edges. Tamam? So the first property is the Euler path. The end point and the start point are different. The second property is something called the Euler cycle. They sometimes call it Euler tour. They sometimes call it Euler circuit. Sometimes they call it Euler circle. All of these are the same. It's a closed, so you start and you finish at the same point. But the important thing is you pass every edge exactly one time. A question for you. Can you find, so we found an Euler path here. Can you find an Euler circle or an Euler circuit in this graph؟ اللي يقول يس يوريني نفسه. يوريني يوريني الباث يعني مش نفسه يعني. So let's delete this so you can see it clearly. Huh? It means you start from one point, you make sure you pass every single edge exactly one time, not more than less. You don't skip anyone, you don't pass more than once over anyone, and you end at the same point that you started from. So that's kind of like closed, right?
Can the two exist together?
Yeah, of course. They can. ها ماشي؟ نسمع كلامك. استنى. نبدأ من دي. خلاص بس نبدأ من دي وخلاص كده؟ اوكي. طيب don't exhaust yourself. There is no Euler circle in this graph. And there is a reason for that. And we'll see that reason in a theorem that will show in the next slide. Okay? Yeah, it has to do with edges بس يعني how do I copy something? خلاص. Anyways, so the next two theorems are about those properties, the Euler path and the Euler circle. Okay. The first one says a connected graph G is Eulerian. Eulerian means what? Has an Euler path or an Euler circle. ارجعوا للسلايد اللي قبلها يا اخوانا. If it has a path, we call it a traversable graph. We don't call it Eulerian. Okay? Eulerian means, if we call the graph Eulerian, it means it includes a circle. Okay? So a connected graph is Eulerian if and only if G is connected. That's number one. And number two, has no vertices of odd degree. Tamam? Go back to the graph that we were looking at and you were trying to find circles in it. Do you have some vertices with odd degrees or not? Yeah, في two of them, A and B, right? There are two vertices in the previous graph that has degree 3. What's the meaning of a degree? What's the degree of a vertex?
Basically, how many is connected to it?
Yeah, how many is connected to it? Tamam. What's the meaning of a connected graph?
All vertices are connected to each other, to other.
Close. هنفوتها لك. Connect. Yeah, that's the general meaning, but it means that starting from any vertex, you can reach any other vertex, right? By simple path. So by a path that traverses the intermediate edges only once. Okay, doesn't cycle, doesn't go across any edge more than one time. And if that's true, regardless on which vertex you start and which vertex you want to reach, then this graph is called connected. Tamam? Okay, so there is a simple path in that graph between any vertex and any other vertex. Okay, that's called a connected graph. So the conditions here says that this theorem is only applied to connected graphs, and it says that if the graph is connected and all the vertices of the graph are of even degree, then definitely this graph has an Euler circle in it. What's the meaning, ya shabab, of if and only if? How is that different from if only? If I say if and I don't say and only if, إيه الفرق? What's the difference between saying here if and only if, and if I said if G is such and such? Which means what? Which means what? لا. In both cases, you have to specify both conditions. It goes both ways. So they call this in mathematics, it's a necessary and sufficient condition, which means that if the graph satisfies these conditions, for sure it is Eulerian. Okay? And if it doesn't, for sure it's not Eulerian. If I said a graph is Eulerian if, and I didn't say and only if, tamam, and I put the conditions, this means that if these conditions are true, the graph has an Euler. Tamam? What if they are false? I don't know. Tamam? That's the difference. Here, if and only if means if the condition is satisfied, the result has to happen. If one of the conditions is not satisfied, the result cannot happen. Tamam? So it's very clear. Yeah, the only way. Yeah, okay? خلاص? Both theorems are if and only if theorems, okay? The second one, the second theorem says that if a graph has an Euler trail يعني Euler path. But the guy here likes to use different English words, okay? So that's not a closed one, that's an open one. You start at one place, you finish at another place, okay? So if it has an Euler trail from node A to some other node B, okay? That's for a connected graph. If and only if, he repeats the word connected again, if the graph is connected and for A not equal to B, those two start and end points are the only two nodes of odd degree. Tamam? So notice it says this. You can have an Euler trail, which means you can have an Euler path starting at node A and finishing at node B, tamam? Passing through many other nodes, okay, many intermediate nodes in the middle, under the condition that A is odd degree, B is odd degree, and all the others have to be even degree. If this condition is true, the point that you start from is odd degree, the point that you end on is odd degree, and all the intermediate nodes other than A and B are not odd, which means they are even, right? Then this means that this graph G that has this property contains an Euler path that can start at A, finish at B. For sure, there is one. Okay? But does it mean we have an Euler graph that starts here and finishes somewhere else?
Not sure. No.
We don't know or no? No, because it's F and only F. And here we are starting at an even point, right? So we cannot start an Euler graph from an even node. خلاص? Go back to the graph that we looked at. We found one Euler graph quickly without really, Euler path, started from A, finished at B. Look at the graph, and of course it can start the other way. Look at the graph and tell me if you can start any other Euler path in this graph.
And from A to B.
لا ما خلاص ما قلنا A to B و B to A. Any other place.
Conditions being transferable and also oriented.
Sorry?
Being one of them.
Yes, it can be. Yeah.
Not applying.
So it can be a cycle, and within a cycle you can find an Euler path. But the other way around doesn't work. If it's only an Euler path, it does not guarantee that you can find a cycle.
So Doctor, how does this help generally? Okay, if I know that it's back at single area, then
ولا حاجة. معناها ان انت تقدر توصل من ده لده without really paying a lot of cost because you don't need to go through multiple goes and back and forth مثلا. Okay.
Especially failure best for both edges.
Yes.
Short distance. ما يعديش ابدا بس
yes. This is traversing all the nodes. لو انت عايز تبعت حاجة لكل الناس يعني. Yes. أو traversing all the edges. Yes. Okay. Yeah, that's a condition. So it's not just connection between A and B, connection between A and B that passes through all the existing path, existing edges in the graph. Yes. Okay. Any other questions يا شباب? Questions? No questions. So this just gives you a sketch if you want to do a proof of the Euler theorems, the previous two theorems, how you can approach the proof. It's not the actual proof, okay? But again, it's just for your own information. We don't care about the approach or the proof or whatever. We are more in the realities using the theorem itself, not proving it. And here, this slide just shows you an example of a bit complicated graph that contains A, B, C, D, E, F. So it contains six vertices and edges connecting those vertices. The edges are not directive, they can go back both ways. But here the arrows are showing you one possibility of an Euler. This is what? If you follow the arrows, you get an Euler what? Circle. Because you start and you finish at the same point. And interestingly here, right, you can start at any point and you can do a full circle. So it doesn't matter where you start in this graph. Okay? عشان لا ملوش دعوه بالسترونج. سترونج بوند ده for directed. This is not directed. This is undirected. خلاص. And it just shows you also the incidence matrix. By the way, why here all of a sudden we are looking at the incidence matrix? Why not the adjacency matrix?
Because we have to
Yeah, so again, you can use any one of them, but we said that when you are more interested about properties related to edges, then the incidence matrix might be more useful for you. Both can work and you can use them, but the one which is easier to deal with is going to be the incidence matrix. If you are more interested in properties related to vertices, then the adjacency matrix is the better tool for you. تمام? That's why in this case, because in the Euler property, we care about the edges, not the vertices. That's why this example gave you the incidence matrix instead of the adjacency matrix. Even though we didn't really use it to figure out the property, but we just had the presentation, the representation there, okay? Now, the second set of properties are the Hamiltonian properties. And as I mentioned at the start, the Hamiltonian is actually more focused on vertices. And you can imagine, it's more or less the same thing. So there is something called the Hamiltonian path, which means that you start at some vertex, you finish at another vertex, and you pass every single vertex in the graph exactly one time. So you don't go across the same vertex more than once or less than one. You don't skip any one, and you don't go across any one more than one. Okay? Now, if this is the condition, by the way, what do you think is going to happen for the edges? Can I pass an edge more than one time? No, no way, right? Because passing the edge means I will pass through its vertices. And if I pass it more than one time, so what can happen?
Skip it.
I can skip some edges, right? It can happen. When I'm looking for a Hamiltonian path, it might, and most probably it will, skip some of the edges as you go through all the vertices exactly one time. تمام? Okay, so the coverage here is about covering the vertices. So, for example, if I care about going through certain cities, then it's more important for me to make sure I cover all the cities that I want to go through. It doesn't matter which road I use, right? On the other side, if I want to cover all the roads because I want, for example, to measure the distances, or I want to rebuild the roads, or I want to like do some renovations or color them or do the lining of the roads and so on, I want to make sure that I go across each road once to fix it, right? Then I care about the Euler property, how to go through all the edges exactly one time. And I don't care if I pass the same city twice or three times. It's not my issue. Okay? تمام?
Isn't like this, or use it make it like a circle?
Which one? لا, because you finish and then you don't go back.
I don't go back to the same point.
No, that's the next one is the circle. So there is a Hamiltonian cycle, there's a Hamiltonian path. We are talking about the Hamiltonian path. If you go to the Hamiltonian cycle, you start at one point, you cover. So, okay, so let's go to the next one. The Hamiltonian circle or cycle or circuit, all of these are used, means that you start at one vertex, you pass every single vertex in the graph exactly once, except the one that you started from, because that one, you have to come back to it one more time to close the cycle or the circle. تمام? So that's the Hamiltonian cycle. Okay? A cycle that visits each vertex exactly once, except for the starting vertex, which is visited once at the start and once again at the end. That's it. So you cannot like choose one, even that start, you cannot pass it, come back to it, pass it. So you visit it 3 or 4 times? No. Only 2 times, the start point. All the others are visited exactly one time. We call that a Hamiltonian circle or circuit, okay?
Doctor, like this, there will be not have 3 connections or any other connections here
For what?
for the Hamiltonian, because otherwise we are kind of looping only when we do a circle we connect at the end.
لا, هي الedges هي اللي كانت cares about not having 3 connections or odd connections وكده. When we look at the conditions or the theorems related to, it's coming in the next slide, okay? When we look at the conditions for those one, it's different. The conditions actually are how many edges are there, and there is a certain minimum number of edges that should be connected to each node so that I can ensure that there is a Hamiltonian circle, okay? We'll see it in the next slide. And next slide, not the next exactly. So this shows you a Hamiltonian graph that includes a Hamiltonian path. So here we have 5 vertices, and we have also 5 edges, connecting them in a certain way. Okay, and you can see that you can start here, traverse all the vertices exactly once, and you finish here, right? So this path is what we call a Hamiltonian path. Notice that I didn't traverse this at all. It doesn't matter. Okay, so I don't care about edges. I only care about making sure that it's a single path that starts at some point, finishes at another point, and goes through each vertex exactly once. Okay, that's a Hamiltonian path. Now, a circle can be found here. Can anyone give me an example of a Hamiltonian circle here? So you start at one vertex, you finish at the same vertex, and you pass every single vertex exactly once. لا لا في لا نو ليه بس فكر شويه بس. ماشي وحتى مش من النص. انا بقول لك انت ممكن تبدا من هنا وتلاقي هاملتونيان سيركل. ها
واحده من الاطراف اللي فوق.
لا سيركل سوري هاملتونيان باث سوري هاملتونيان باث سوري سيركل نو. So first of all, let's focus on the circle. Can you find the Hamiltonian circle here? Yeah, so your answer is correct for that. There is no Hamiltonian circle. تمام. What about a Hamiltonian path? Where? من هنا وبعدين كده وبعدين كده وبعدين up ولا تحت؟ up ولا تحت؟ طيب up here and then we finish here, right? So this way we have passed through all of them exactly once. Okay. Okay. I'm not going to spend a lot of time on this slide. This slide is more related to something called complexity analysis, which is part of algorithms theorem. If you have a particular problem and you have something that you measure the size of the problem with, and in this case, in the case of graphs, for example, you measure how big or how small your graph is, mainly based on how many vertices are in the graph. So a graph that has 5 vertices is actually a small graph. A graph that has 1,000 vertices is a very large graph. Okay, 10,000 is even a much larger graph, and so on. So the measure of the size of the problem at hand, which is finding something on the graph, is the number of nodes in that graph. Okay, now in order to find something on the graph, like a certain path or a certain property or a certain cycles or whatever we have been looking for, you need to analyze that graph. You need to search, for example, in the previous slide, we had to kind of by our eyes search where is a Hamiltonian path, right? So, but there are typically some methodologies, some systematic methodologies that allows you to find those things that you are looking for. Okay? Those methodologies are done by doing some computation and some analysis of the graph, right? Any process that includes computation and analysis will go through a certain number of steps, right? The number of steps that you do in order to solve the problem is called the complexity of the solution. Tamam? So, if the size of the original problem, like the number of nodes, okay, appears in the equation that tells you how many steps you need to do to solve the problem. If it appears there as a polynomial, like for example, to find the total number of Hamiltonian paths in a graph of size n, I need to do computations in the order of n cubed. The amount of computational steps that I need to do is going to be n to the power 3. This kind of problem is called a polynomial problem, and that's actually good, not bad. Any good computer should be able to scale, even if your problem has 1,000 path, 1,000 vertex, right? 1,000 to the power 3 is what? لا مش قلط ولا حاجه، ده رقم عارفينه. ها اللي هو كام؟ بنقول عليه ايه؟ 1 جيجا 1 مليون ايه يا اخوانا؟ 1000 to the power 3. 1 بليون يعني 1 جيجا. مظبوط؟ 1 جيجا operations can be done on a good computer and can be done quickly, right? Okay. So scaling as a power of, as a polynomial of the size of the problem is manageable. Then this problem can be solved with good computational capabilities in a very short time. تمام؟ The problem happens when the scaling is exponential. So n appears in the power, not in the base. Okay. So if the problem is of size n and the solution is to e to the power n, the number of steps, then as you grow, when it reaches 1,000 steps, what's e to the power 1,000? That's a big number. We cannot say it, right? So e to the power 1,000 is really, really, really a large number. Okay? So in that case, the non-polynomial scaling, the exponential scaling, causes this problem to be very hard to solve. Okay? So in algorithms, and even because solving graph theories always comes with a certain algorithm that allows you to go through the graph, and we will see one example of those algorithms towards the end of the lecture today. You go through the graph and then you compute something to figure out a certain solution that you are looking for, right? Okay. So if that solution is very hard, we call the problem non-polynomial hard, NP hard, or if it's even like 100%, like there is no even randomized approach that will make it easier, then we call that NP complete. It's definitely non-polynomial, no matter what you do. Okay? Now, this slide is meant to tell you two things. This thing that I just explained, and how do we figure out if a particular problem is really hard, so NP hard or NP complete or not. One of the best ways to do this is by doing something called mapping. Okay? What is mapping? Mapping is looking at the problem at hand and trying to see if it corresponds to another problem that we know already that it is hard. Okay? And if we can find that one-to-one mapping, similar to the isomorphism that we discussed earlier in the case of graphs, right? If we can find this one-to-one mapping between the problem that we are investigating and a problem that has been shown to be NP complete or NP hard, then this is sufficient proof that definitely this problem is also NP complete or NP hard. Tamam? That part is a very specialized part. The slide here is for you as engineers when you later on work somewhere and you hear some people saying, oh, this is an NP complete problem, this is an NP hard problem, this is very difficult to solve. You know that there is a branch of mathematics that you probably need to go and ask ChatGPT about or read about or whatever that tells you how to do that. Okay? So just that the word makes sense to you. But we are not really gonna investigate anything in terms of hardness or completeness or whether it's non-polynomial or polynomial or not. Okay? طيب عندك question؟ مش هسألكوا فيه، تسألني انت ليه؟ طيب خلاص كويس. انا مش هسألك، انت ما تسألنيش خلاص. Okay. A couple of other important theorems related to the Hamiltonian graph. I'm coming back to your earlier comment. So there are two theorems again for the circle or the Hamiltonian circle and the Hamiltonian, both of them actually are for the circle. So we don't have theorems, we are not studying theorems for the Hamiltonian graph, path, okay? But there are two ways to figure out if there is a Hamiltonian circle or not in a particular graph. The first one says that it's called the Dirac theorem, and it says that if you have a graph G, which is simple, what's the meaning of a simple graph? Simple graph يعني ايه؟ طيب, simple graph, we said it not the last lecture but the one before, it's an undirected graph. So remember, simple path is a path that doesn't traverse the same edge twice. لكن simple graph معناها undirected graph. Very easy. تمام؟ Okay. So if a graph G is a simple graph, which means it's an undirected graph with number of vertices n, and n is greater than or equal to 3, so like a sizable graph, like n equal to, doesn't include cycles or anything, right? It's just 2 points, right? So with n greater than or equal to 3, such that the degree of every vertex in G, so if you go across the vertices of that graph and you count the degree of that vertex, so for each one of them, and all of them satisfy that they are greater than or equal to n divided by 2, n is the number of vertices in the whole graph, right? And the degree of each one of them is greater than or equal to n divided by 2, then for sure this graph has a Hamiltonian circle. You can find a Hamiltonian circuit in that graph. Okay, so what are the conditions? Undirected graph, the size or the number of vertices is equal to n, which is greater than or equal to 3, right? And the third condition is every single vertex has a degree greater than or equal to n divided by 2. تمام? If those conditions are true about a graph, definitely the graph has a Hamiltonian circle. طب what if one of the conditions is not true? We don't know. لأن there is no if and only if. Right? It says if the condition is true, then there is a circle. What if it's not? I don't know. There might be, there might not be. Okay? طيب. Second theorem or theorem says that if you have a graph which is simple with n vertices again, and n is greater than or equal to 3, and you choose any 2 points on that graph, any 2 vertices on that graph, you measure the degree of those 2, you add it together, and that sum of the degree of any 2 vertices u and v is greater than or equal to n, right? The sum of the 2 degrees of those 2 vertices is greater than or equal to n, and those 2 vertices are not adjacent. So u and v are not adjacent. They don't have an edge between them. تمام? If this condition is true for all u and v that are non-adjacent across the whole graph, then for sure the graph has a Hamiltonian circle. Okay? If the condition is not true, we don't know. So there are 2 ways that if one of those 2 conditions, theorem 1 or theorem 2, happens in a graph, then you can say, I'm sure that this graph has a Hamiltonian circle. If both of them do not exist, you don't know. Okay? It might have, it might not have. Okay? Do you understand the second one? How you will do it? If I give you a graph, how can you use the second theorem to test? What will you do?
Calculate the number of nodes. How many?
أيوة. So the first thing is you want to know how many vertices are there. So figure out n. Okay, وبعدين and then
Like this. I take 2 nodes and calculate how many,
degrees. Okay.
then add them. If they are bigger than n or equal to n, then we have
لا. What you said is true, but it's not a complete check. The complete check, you have to go across every 2 nodes that are not adjacent to each other and make sure that they satisfy this condition, because it says for every pair of non-adjacent vertices. So you have to do this for any u and v that are not connected together. By the way, if I give you a graph, how can you, from the matrix representation, find quickly how many, yeah, exactly. خلاص هو answered قبل ما اسال السؤال. How many pairs of u and v are there? But from the zeros, again, doing what with the zeros? Just counting the zeros? over 2 كمان، وفي حاجه كمان.
لازم تعد الكولمز والروز.
ماشي، عشان كده قال لك اوفر 2 عشان هي هتتكرر مرتين. and the diagonal is not part of your calculation because the diagonal is always 0 unless you have loops, right? So the diagonal also is not part of your calculations here, and loops are not part of this theorem. Okay, so if you want to know how many, first of all remove the number of the diagonals, that's not counted, and then look at all the other ones, count the number of zeros in the rest of the matrix divided by 2, or count the number of zeros in the lower triangle or upper triangle of the matrix. بس تمام. That will tell you where are those pairs of non-adjacent nodes. Yes.
But I don't understand the direct theorem because, for example, we have this circuit, many vertices, one another. Like going up and around, and you have 20 vertices, and then n over
No, sorry, بس انت you started from where? Okay.
we go around.
Okay. Okay.
So
This is بس انت you are testing theorem 1 ولا 2 عشان ابقى عارف. theorem 1. Okay.
but n over 2 is 10. And only this one.
So you started from here, you took a round which passes through all the vertices, and then you end up, okay. Okay, so what's the problem?
That n over 2
Yeah,
should be
yeah,
this.
yeah, yes. So,
3
yes, but the theorem doesn't say if and only if. I already explained this, right? So it says if the condition is true, you are sure. If the condition is not true, I don't know. You can try something like what you did and you find something. تمام؟ Okay, يا شباب. Question. Thank you. Now the last thing, and I don't know if we'll have time to solve problems. Maybe we'll do it all next time. So the last part is some very important algorithm that goes through a graph and tries to find something called the shortest path. Okay. And before going through the description of the algorithm, I'm not going to elaborate that much on the description, but I will give the general idea, and then we will look at an example that will give you a very clear idea how the algorithm works. But before going through it, we have to understand what is the meaning of a shortest path between two vertices on a graph. Okay, shortest path is a path that minimizes a certain criteria that I put myself for how costly is a path. So it doesn't necessarily mean that it's the path with the less number of edges, not necessarily. And we'll see that in the example. Okay, there is something like, okay, if I talk to you directly through some phone line, the cost of the conversation is going to be 10 riyal, for example. However, and we do that, by the way, if I call you with regular phone when I'm roaming outside, the cost is maybe 100 riyal or something if I have a long conversation, right? And that call is probably going to pass through from my cell phone to the base station, to the core of the network there, directly to the core of network here in Qatar, base station closest to your cell phone, and then to you, which is like 5 hops, right? But it costs 100 riyal. On the other side, if I use voice over IP, something like WhatsApp voice or Google Meet or whatever, right? The whole call is going to cost me almost nothing. Or if I pay for my data with some good rating for the roaming data, maybe something like Uridu Passport or something like that that you do when you travel, then the call is going to cost me something like 5 to 10 riyals. Okay? Even though in that case, when you inspect, you will find that the call went from your phone to the base station, core of the network, and then at the core of the network, it went through the internet data connectivity, so through hundreds of routers, and then hundreds of routers here in Qatar, and then eventually to your phone, either through Wi-Fi or through the cell phone network, depending on which one you were using for your connectivity, right? So the number of intermediate edges and vertices are much larger, but the cost is smaller. In that case, we call the second path the shortest path because it's the one that minimizes the criteria that I'm interested in. So you always have to look for what is the criteria. Is it cost? Is it speed? Is it delay? Is it number of hops? So that is something to keep in mind, okay? خلاص? So the definition of a shortest path depends a lot on how do you calculate the length. Is it just how many hops? Or the length is actually how much it costs me? Or the length is how much delay it incurs into my communication, okay? خلاص? Now, the Dijkstra algorithm, which is given a particular network, that algorithm is capable of, when you define for it a start point, a start vertex, it will traverse the network, it will kind of do some computations in the network in order to be able to find out what is the shortest path between this start point and every other vertex in the network. That's what the Dijkstra algorithm is doing. And if you imagine, if this algorithm is running on every single point of connectivity, like the routers, for example, okay, then it will do this for every router. It will assume that this is the start point, and I can find the shortest path to all the other points in the network. Then the network, in this case, can work in an efficient way, right? Whenever you want to communicate from one place to the other, your packets will take the shortest available path at this moment. And the algorithm itself works in something called the greedy approach. Greedy approach meaning that you approach the problem by looking at just one step and figure out what's the minimum during this one step that takes me from one point to the next one. And then at the next one, you do the next step of calculation, find out the smallest, and so on, hoping at the end you solve the whole optimal problem completely from start to end. Okay? All of this is abstract talk. Now let's look at an example that will clarify how does this work. Any questions at this point before we look at the example? Okay. Fine. Slides and even a theorem, it's not that important. And here a example that shows how the algorithm works. The initialization of the Dijkstra algorithm is shown in the upper figure that you see up to the right in the slide here. So this is your start point, point S, okay? You didn't run the algorithm yet, you just kicked in. The algorithm is gonna assume that the distance, the cost to reach any other point in the network is equal to infinity. So it will say, I need to pay infinite cost to get here, infinite cost. So it will label all of them as far away, I cannot reach them. They are all out of reach, very costly, right? And then it will start. Before going through the algorithm, notice that each link has an associated cost. This is something given to you. This is part of the design of the network, which is given to you, right? That cost can be that it has more delay. Maybe the link with the higher speed will cost more money, so you will put higher cost for that link. Or maybe you care about speed, so the link with higher speed will be less costly for you because it doesn't slow down your communication. It depends, right? But anyways, the algorithm starts from given cost for each link. So each edge in the network has an already given cost. Okay, these are the numbers that you see up there. Okay. And then the first thing is step number one. We said greedy, right? So okay, from my start point, what can I reach? I can reach this guy and this guy. How much I will pay? So this is what we see here. To get to this, I will pay 5. So the cost of this is equal to 5, right? To get here, I will pay 10. So the cost of reaching this is equal to 10. Step one finished, okay? The other ones, I didn't test them, so they stay as infinite. I don't know, okay? Far away, I cannot reach them. Next step is gonna go for point X and point U and investigate further what can be reached from those, okay? Let's look at point X. Remember, I was able to reach this, right? Through this link at a cost of 10. And the last thing was registered as 10, okay? Now, when I investigate from point X, I can see that I can add 2 to reach here. So I can reach this one with 7. So I remove the infinity and I put 7. And the path to reach from S to here becomes this one at a cost of 7, right? This point used to be at infinity. Now when I do the calculation, I can see that I can 5, and then I add 9, the cost of this link. So I reach here with a cost of 14. And that's the only path I found so far. So I will put this as 14, and the path to reaches is gonna be this way. Interestingly, I find that I can also reach U from here. So I can reach it from S through this combined path at a cost of 8. And the direct was 10. So now this path is no longer important because it's higher cost. I will remove it. I will also update this to be at 8, not at 10. Okay. So now at this stage, reachability of U through the shortest path I calculated so far is this one at a cost of 8. Okay. Repeat the same operation. So go to this point. Okay. What's new here is that we did a calculation at point Y. So let's see what happens from Y. From Y, I can reach point V. Okay. Remember, I was able to reach point V earlier at a cost of 14. Now, if I reach it from here, it's 7 plus 6, 13. So this one is no longer needed. So it disappears. And now reachability for V is only through this path because that's the lowest cost so far. Yes. ما هو ده جاي لسه في الستيب الجاي. You did not investigate you لسه. Okay. But you are right. Okay. So that is اللي مؤمن قاله. Right. So now I go to you and investigate. Right. When I am at you, I can reach this. By the way, all the lines here are directed. Okay. So it's one way when we are doing this. The graph is given this way. It can be two ways, but here it's one way. So I can reach from U to V, right? Through a cost equal to 1, which means that the total now at V, rather than being 13, became 9. So I no longer need the way that takes me there at the cost of 13. I can reach there at a cost of 9. You can imagine you keep doing this at every single node of the network, you will end up with a final setup as we see it here, right? Where from S, you know exactly what's the shortest path to X, and it comes at a cost of 5. What's the shortest to U, and it comes at a cost of 8. What is the shortest to Y, and it comes at a cost of 7. And what is the shortest to reach V, and it comes at a cost of 9. And if you do this for every other node in the network, you have that table in each interconnection point that tells you if you have something going in that direction, then the direction for the least cost is to take it to that next link. Remember when we discussed this earlier about how the routers figures out which way to put the packet? This is how they build those tables through the Dijkstra algorithm. And this is how eventually they figure out, given the current network configuration, what is the right way to take the packet so that it can reach its final destination at a minimal cost, whatever the cost is, okay? Now, this algorithm runs across the network using some protocols within the IP layer. We will come to that later when we discuss the TCP IP. Those protocols are responsible for exchanging how much is the cost and did the packet actually reach you or not, to discover how many nodes are there so that you can know the configuration that you want to build your routes on. And every time a change happens in the network, there is some part of the protocol is to raise some flags that tells the intermediate nodes to go and update their table because they need to do recalculation. The network has changed, right? So they go and update the table of routing. Yes? It depends. I mean, efficiently, you should know which part the change is affecting, and they only need to do local calculation. Sometimes you need to do a much larger scale calculation. But again, this gets executed. Yeah, it uses some resources, but gets executed pretty fast. Okay. Yeah. It depends. Sometimes going through a particular node has its own cost as well, so you can add also the cost of being at that node. Yani here, the numbers inside the node are not representative of an added cost of the node. It's just a representation. The numbers here are just a representation that the path that takes me here costs this. Tamam? It might be also that there is maybe, for example, there is some processing cost that you have to pay for the node. So this number will have something added to it since you are at that node. Tamam?
This is like the cost function which analyzes, like, for example,
So what you are talking about is how we formalize this problem as an optimization problem. That's what you are talking about. So we put some cost function that says if you do something wrong, you will pay more. If you do something less, you will pay less. Okay, or do something better, you will pay less. But what we are discussing here is a solution of such problem in this particular situation, the situation of trying to find the shortest path. Okay. Any other questions, ya shabab? Yes. Not the packet knows. The intermediate nodes already know. So if a packet, for example, comes from somewhere to this node and the destination address is this node, for example, it knows now that it should send it this way. Right? And then for this one, it will know that it should send it this way. And for this one, it will know that it should send it this way. Okay, so the packet is going to go through this path because that's the shortest one to reach here. not the packet updated. Imagine, for example, this network, one of the connections is broken. So now the table that exists here that tells me I can reach here at this cost is no longer valid. So what do I need to do? I need to go and recalculate the shortest path given the current new configuration of the network. No. This is done before. At the packet, when the packet is sent, all what I do is look up in the table and I will find the path already there. It says it has to go here, right? But the calculation happens before packets. That's during configuration of the network. Okay. Any other questions?